Hello, this is Charlie Thompson, and welcome to Lab 6 on humidity. In this lab, we'll learn how to find maximum specific humidity, find dew point temperature, calculate relative humidity, calculate and evaluate the specific humidity deficit. So let's go over some definitions. Humidity is water vapor in the air. Water vapor is the gaseous form of water. It is exactly in the atmosphere like oxygen, like nitrogen. I mean, the fact that it's when a liquid, we're able to drink it is weird, but when it's in the atmosphere, it behaves just like all the other gases in the atmosphere. The maximum amount of water vapor that can be present in the atmosphere is a function of temperature. The higher the temperature, the more energy available to evaporate water, and the more water could be evaporated at that temperature. It doesn't mean you have that water, but there's energy to evaporate water. Saturation is the term for when the relative humidity is 100%. If the air is filled with water, which is completely wrong, I can't even say that, I'm going to have to back up. Saturation occurs when the relative humidity is 100%. When all of the energy available to evaporate water has been used up evaporating water, so there's no more energy left to evaporate water, the air is saturated. If you add more water, you get condensation. If the air cools even slightly, you get condensation, because when the relative humidity is 100%, the maximum amount of water vapor present in the atmosphere is how much is present, and there's no more energy for any more water vapor to be present. Dew point temperature is the temperature at which a given mass of air is saturated. The way we're going to abbreviate this in this lab is TDP is the abbreviation for dew point temperature. You can think of temperature, comma, dew point. That might help you remember what it is. It's, I think, the only little abbreviation we're going to use that might throw you for a loop. If the dew point's below zero, it's given as a frost point because the water vapor will sublimate out and become ice directly. It won't condense and become liquid if it's below zero. Some examples of frost and condensation. Clearly, in both cases, the atmosphere, the air was saturated. Otherwise, the frost wouldn't have sublimated. Otherwise, the water vapor wouldn't have condensed out on the glass. So, specific humidity. Specific humidity is a measurement. It's a way of expressing how much water vapor there is in the atmosphere. There's a bunch of different ways of doing it. We're going to look at three today. We're going to look first at specific humidity. And specific humidity is just how much water vapor there is. It's the mass of water vapor in grams per mass of air in kilograms. It just tells you how much water vapor is present. It doesn't tell you how much there could be at that temperature. It doesn't tell you as a function of anything else. It just tells you this is how much water vapor you have. And a kilogram of air has a volume of about a cubic meter. So if you imagine a blob of air 3 feet by 3 feet by 3 feet, that would weigh about a kilogram. And so when we're talking about grams of water vapor per kilogram of air, imagine that floating 3-foot cube of air. So this is a chart of maximum specific humidity. Every place on this line is the maximum water vapor possible at that temperature. So across the bottom, negative 40 Celsius, negative 30, negative 20, negative 10, 0, 10. It's got temperatures in Celsius and in Fahrenheit. And along the left-hand side, it has grams of water vapor per kilogram of air. And there's a handy note that says every 10 Celsius increase in temperature just about doubles the maximum specific humidity. So at 0 degrees, there's enough energy to evaporate 4 grams. At 10, it's about 8. If it warms another 10 degrees to 20 degrees, there is enough energy to evaporate 15 grams. At 30, it's about 27 grams. And finally, at 40 degrees, there's enough energy to evaporate and keep evaporated 47 grams of water vapor, which is almost 2 ounces. That's a quarter cup of water. So at 40 degrees, which is 104, there's enough heat energy to evaporate about 2 ounces of water for every 3-foot blob of air. And again, this is the maximum. It doesn't mean you have that much. It's just telling you at 0 degrees, the maximum amount of water vapor you could have present is 4 grams. Here's another chart. This is out of a different textbook, and I thought it would be handy for you because it's got a table that makes the relationships a little bit more concrete. You don't have to guess. At 15, what am I looking at? I don't know. At 15 degrees, the maximum is 10.6 grams. At 20 degrees, the maximum is 14. We'll talk more about that table in just a minute. We'll talk about it right now. So if you know the temperature, 25 degrees Celsius, you go up till you hit the line, and then you go over to the left. You go up till you hit the line, then you go over to the left. So at 25 degrees Celsius, the maximum specific humidity is 20 grams. So another way of doing it with a chart, if you know the temperature, or if you know how many grams you have, 20 grams, then the dew point temperature for that is 25 degrees. So it goes back and forth. Let me back those up for just a sec. So if you know the temperature, 25 degrees, you can find the maximum specific humidity. Oh, man. So this is a chart of maximum specific humidity. It's a slightly different chart with a table. I thought that might be helpful so you don't have to guess. And here's how you can figure out, here's how you use the table or the chart to find maximum specific humidity if you know the temperature. So for example, if it's 25 Celsius, you go up till you hit the line, and then you go over to the left. So at 25 Celsius, the maximum specific humidity is 20 grams of water vapor per kilogram of air. You can also find the dew point temperature. If you know that you have 20 grams of water vapor per kilogram in the air, the dew point temperature for that is 25 degrees. Another way of thinking of that is, if it's 25 degrees, the maximum specific humidity is 20 grams. If you have 20 grams, the dew point temperature is going to be 25 Celsius. So you find the temperature, slide to the left to find grams of water vapor. So this is a short version of the table that you'll have access to do this lab. I've got a table broken down by every Celsius degree between, I think, -40 and +40, so that you don't have to guess. You don't have to wonder, well, if at -5 it was 2.8 and at -10 it was 1.8, but now it's -7, what is that? Just use the table. So using this table, you read the maximum specific humidity, for example, 10.6 grams. So if you were given a problem and I told you the specific humidity is 10.6 grams, what's the dew point temperature? You find the maximum specific humidity, and then you slide over to the left to find the dew point temperature. So the dew point temperature, if you have 10.6 grams of water vapor, is 15 Celsius. You can also use the same table to find the maximum specific humidity. So if you know the temperature, 0 degrees, you just slide over to the right to find the maximum specific humidity. So at 0 degrees, the maximum specific humidity is 3.8 grams per kilogram. Saturation vapor pressure is the amount of water vapor in the atmosphere expressed in millibars, just like we were using to express general atmospheric pressure. So vapor pressure is the part of the atmosphere that is water vapor expressed in millibars. Water vapor is just one gas in the atmosphere. Here is a chart of saturation vapor pressure. So again, it's very similar. Every time you go up in temperature, the saturation vapor pressure just about doubles. Every 10 Celsius increase, the saturation vapor pressure just about doubles. I'm sure there's got to be a conversion factor between saturation vapor pressure and grams of water vapor per kilogram of air. We're not going to use saturation vapor pressure, but I think it's important to talk about because you'll come across it and you should know what it is. So saturation vapor pressure, it's just another way of measuring or expressing, not measuring, but expressing how much water vapor there is in the atmosphere. Speaking of expressions of humidity, relative humidity is the third. So we saw specific humidity and maximum specific humidity. We saw vapor pressure, and now we've got relative humidity. Relative is related to something else, right? So it's how much water vapor is present, how much do you have, compared to how much you could have expressed as a percent. So the amount present is how much you have. The amount possible is just a function of temperature. So you'd have to look it up on the table, or I'd have to give it to you. So examples of relative humidity on an actual day. It's first thing in the morning, 0 degrees out. The maximum is 4 grams. You have 4 grams, so the relative humidity is 100%. If it warms up by 10 degrees, the maximum is going to increase to 8. You still have 4, but the maximum is now 8. So the relative humidity is 4 divided by 8 times 100 would be 50% relative humidity. Notice that when the maximum increases, the specific doesn't increase. Just because it gets warmer and there's more energy to evaporate water doesn't mean that you have more water to evaporate. You could be in a dry region where all of the water vapor has already evaporated. So just because the maximum increases, it doesn't mean that the specific humidity is also increasing. So if it got warmer by another 10 degrees, the maximum would increase to 16 grams. You have 4, the max is 16. 4 divided by 16 times 100 is 25%. So now the relative humidity is 25%. As the day goes on, the sun sets and it starts to cool. If the temperature drops by 10 degrees, the relative humidity is going to double because the maximum has been cut in half. The max was 16, now the max is 8. 4 over 8 is 50. So the relative humidity, as the temperature drops, is going to go up. If it gets colder by another 10 degrees, 0, now the relative humidity doubles again from 50% to 100% because the maximum has been cut in half. As the temperature warms by 10 degrees, the maximum specific humidity just about doubles. As it warms by 10 degrees, the maximum just about doubles. As it gets colder by 10 degrees, the maximum gets cut in half. As it gets colder by 10 degrees, the maximum gets cut in half. So as it gets warmer, typically the relative humidity gets lower. In fact, this is going to be very, 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 very important in the assignment that you're going to do, which is going to look at the fires in Oregon in August or September. And one of the things that made the fires so bad was, just like we have Diablo winds and Southern California has Santa Ana winds, the winds came over the mountains and flowed down slope. And as they flowed down slope, the air got compressed and it heated up. And so as the air heated up and heated up, the relative humidity kept dropping and the air got relatively drier. The specific humidity stayed the same. So the actual amount of water vapor stayed the same, but the maximum got bigger and bigger and bigger as the air got warmer and warmer and warmer, so the air got drier and drier and drier. So the relationship between temperature and relative humidity is a really important one. In fact, I should mention, this is why weather forecasters, well, they tell us what the relative humidity is because it determines how comfortable we are as humans. If it's too dry, we get ashy. If it's too moist, we're all sweaty. So they'll tell us what the relative humidity is. Weather forecasters typically just pay attention to specific humidity. If you know the specific humidity and the temperature, it's very easy to calculate out what the relative humidity is. We'll do a lot of that in lab. And so because the relative humidity changes with temperature, but the specific humidity doesn't, weather forecasters really pay attention to what the specific humidity is, and then they just tell us what the relative is because that determines how comfortable we are. So same deal. If the specific humidity remains the same, so this we've got a chart of temperature, lower and higher temperature, and then relative humidity, higher relative humidity, lower relative humidity. This is actual charting from the Sacramento airport. So the time of day where there's the highest temperature, because that's the time of day when you'd have the maximum specific humidity, but your specific humidity probably hasn't changed, highest temperature, lowest relative humidity. When the temperature increases, relative humidity decreases if the specific humidity stays the same, which it usually does. So if the specific humidity remains the same, but the temperature decreases, so if the temperature drops, then what's going to happen is the relative humidities go up. So the specific humidity is staying the same, but as the temperature drops, the maximum specific humidity also decreases. So now you have the same amount, but the maximum is less. So your relative humidity increases. This is just a chart showing maximum, or the actual amount of precipitable water. This is water vapor in the atmosphere, and you can see under the ITCZ enormous amounts. Over the cold places, not a lot of water vapor. If it's hot, probably a lot of water vapor. If it's hot with a warm current, lots of water vapor. If it's the same temperature but with a cold current, much less water vapor. In fact, here are the world's deserts under the subtropical high, subtropical high, subtropical high, subtropical high, subtropical high. So measuring humidity, this is a sling psychrometer. As water absorbs heat, it evaporates, which cools the thermometer. So a sling psychrometer has two thermometers. One of them has cotton wick that you get wet. The other one is dry. That's the dry bulb. The one that's wet is the wet bulb. It's on a handle and you spin it around. As you spin it around, as water evaporates, it absorbs heat from the thermometer. The water vapor evaporates, taking the heat with it. So the more water evaporates, the more the wet bulb cools. So you spin it around and then you compare the two temperatures. If there's a big difference, it means that there was lots of evaporation, so there was lots of energy to evaporate water, so the relative humidity is low. If there's a big difference in temperature between the wet bulb and the dry bulb, that means that there was lots of evaporation, so the relative humidity is very low. If the temperatures are the same, that would mean the relative humidity is 100%. There's no spare energy to evaporate water. It's all been used up in evaporating water. So if there's no more energy to evaporate water, no more water evaporates, there's no more cooling of the wet bulb, and so the temperatures would be the same. So the closer together the temperatures are, the higher the humidity is. The farther apart the temperatures are, the lower the humidity is. No evaporation, no cooling, no temperature difference, the relative humidity is 100%. There's a big difference, low relative humidity. This is another device. This is like the coolest photograph of one of these that I've ever seen. This is a hair hygrometer, and it actually has strands of human hair, and they're attached to this little wheel with a needle on it. And here's the way this works. As hair absorbs moisture, those of you that have hair and have been to San Francisco or the South or someplace with high humidity, you know as your hair absorbs moisture, it gets curlier and it contracts. So the way this works is, as it gets humid, the hair contracts, which then pulls up and tilts the little needle down. As it gets drier, the hair would stretch, and so the needle would point to the dry part. But I think it's crazy. In fact, this was used up until the 1960s. This was the one of the main methods that we used to actually measure water vapor in the atmosphere was a bunch of strands of human hair, which is really weird. All right. Calculating humidity. Now let's get into the practical stuff, and I need to go over a couple definitions. So here are the elements of information that I will provide to you, depending on what the question is. So SH is specific humidity. That is just how much you have. How much you have, specific humidity. Relative humidity is how much you have compared to what the maximum is at that temperature. So specific humidity is going to be expressed in grams of water vapor per kilogram of air. Relative humidity is going to be a percent, and it's the percent toward saturated that the air is. There's the temperature, there's the dew point temperature, and then relative humidity and specific humidity. So those are the temperature, dew point, relative, and specific. Those are the four things that we're going to be playing around with. So relative humidity, it's the amount of water vapor present divided by the amount possible times 100 as a percent. So the amount present, it's just how much you have, expressed in grams. The amount possible is the maximum you could have, also expressed in grams. So to find the maximum specific humidity given a temperature, well, because if we're going to calculate relative, we need to know how much we have, and we need to know how much do we have compared to how much we could have. So let's find the maximum specific humidity. If I give you the temperature, you can find the dew point temperature. If I tell you the specific humidity, you can find the dew point temperature. If I give you a temperature, you can tell me what the maximum specific humidity is. You should be able, at the end of this, to calculate relative humidity given specific humidity and a temperature. You should be able to calculate specific humidity, so how much you have given the relative humidity and a temperature. And then finally, we're going to calculate the maximum specific humidity deficit, which is important in fire weather. We'll tackle that at the very end. So relative humidity, what do we know? It's 25 degrees out and we've got 10 grams of water vapor. So we go look it up on the chart. At 25 degrees, the maximum is 20 grams. Okay, so we have 10, the max is 20. 10 over 20 is 0.5 times 100 equals 50%. So if we have 10 grams of water vapor and the maximum is 20 grams, the relative humidity is 50%. If we know the relative humidity and the temperature, we can calculate the specific humidity, because the specific humidity is just how many grams of water vapor is present. So if I asked you to find the specific humidity and I gave you the relative humidity and a temperature, for example, it's 25 degrees Celsius, the relative humidity is 50%. So in the labs that we're going to do, this is the way I'll set them up. I'll give you, for example, the Oregon fires example. We'll know what the temperature was and we'll know what the relative humidity is. And so we'll have to figure out what the specific humidity is and then the specific humidity deficit. So at 25 Celsius, the max is 20. So at 25 Celsius, the max is 20. We know the relative humidity and the temperature. It's 25 Celsius with 50%. 50% relative humidity means that we have 50% of the maximum. The maximum is 20 grams. Specific humidity is 50% of that. So 50% of 20 grams is 10 grams per kilogram. So if I gave you a problem and said it's 25 Celsius outside, the relative humidity is 50%, what is the specific humidity? You'd look up what the max was, take 50% of that, or whatever the relative humidity is for that problem, and then 50% of 20 grams, in this case, is 10 grams. So the maximum specific humidity, right, yeah, I thought about different ways to try to explain this. I thought about, well, I could try to explain it. It's like, yeah, and then I said I'll just do it. So it's the difference between what you have and the maximum. It's like your gas tank, right? It would be the difference between the amount of gas you have and how much to make it full. So the emptier your tank, the bigger the fire risk. That's pretty much why we care. The drier the air is, the easier fires spread. And one of the tools, and I didn't realize this until just recently, one of the tools that they use is actually, well, here's reality. They used the vapor pressure deficit. I figured instead of going off on an entire third part to this lab, we're just going to use specific humidity because it's just it's an expression of humidity. They're all valid. It's just, are you expressing it in grams of water vapor per kilogram of air, or are you expressing it as a partial vapor pressure of the atmosphere, expressing it in millibars? So the way you're expressing it really doesn't matter. The important thing is, how dry is it? That's what we want to know. So maximum specific humidity deficit is the difference between what you have and the maximum that you could have. And the bigger the deficit, the more dangerous it is for fires because the drier it is. So if I gave you, it's 20 degrees out, the specific humidity is 10 grams per kilogram. So you look it up. The maximum is 20. So then the deficit would be 10 grams. We have 10 grams, the maximum is 20, so the difference between 10 and 20 is 10 grams. So if I gave you, temperature is 30 degrees Celsius, the relative humidity is 15%. So if I give you the temperature and the relative humidity, from there you can calculate the specific humidity, because we know that we have 15% of the maximum. And then the deficit is going to be the opposite of what the relative humidity is, right? So if 15% is how much water vapor you have, then 85% is the deficit. Although I'm not going to ask you in percents, but so it's 30 degrees. The maximum is 27.1. You'd have to look it up on the chart. So the specific humidity is 15% of 27.1 grams. So 0.15 times 27.1. Oh, right. So for all of these problems, and I will put it in the lab, in the actual lab assignment and in the pre-lab quiz, for all of these, we're going to round relative humidity to a whole number. And so relative humidity, we're always going to express it as a whole number, 15, 16, not 16.1. It's close enough. 15%, great. And then for specific humidity, we're just going to round to one decimal place. So the way to round, or rather the way to express 4 grams to one decimal place is actually 4.0 grams. So if the last number is a 0, or rather if the decimal, if the tenths unit is a 0, you express it. I will be looking for that on the quiz, although it'd be weird if many of them were even, like exactly 4 grams. But if they are exactly 4 grams, you're going to need to enter it as 4.0 grams on the assignment. So the specific humidity is 4 grams. The maximum deficit, the maximum specific humidity deficit is maximum specific humidity minus the specific humidity. So the maximum is 27.1. The specific humidity is 4. So the maximum specific humidity deficit is 23.1 grams. That's it for the information part of Lab 6 humidity. There's a pre-lab quiz that will make sure that you're good to go on all of these concepts. You've got the basic ideas down. There's a discussion question about what did you find most challenging about this lab. And then finally, there's going to be a lab activity calculating humidity, specific humidity, relative humidity, and then the maximum specific humidity deficit. That's it for this video. I hope you enjoy Lab 6 on humidity.